Hello dear chemists. Now in this discussion we are going to be looking at another problem in chemical equilibrium. So this problem involves using Kp, which is the equilibrium constant in terms of partial pressures. So at a certain temperature, ammonia NH3 partially decomposes into nitrogen gas and hydrogen gas. Ammonia was added to an empty container until the partial pressure of ammonia reached 0.85 atmospheres. At equilibrium, the partial pressure of hydrogen was found to be 0.45 atmospheres. What is the partial pressure of ammonia at equilibrium? Now let's look at this problem and provide a solution to it. So we're going to say let the partial pressure, let the change in partial pressure be x. So the equation is written as this. We have ammonia gas, which is decomposing to give nitrogen gas and hydrogen gas. So we are putting a 2 here and a 3 here to balance this equation. So we are again going to be using ICE acronym to represent the initial concentration. Okay, since we are talking about pressures, we're going to be saying the initial partial pressure of ammonia, initial partial pressure of nitrogen, and for hydrogen. So let's put I here. So the initial partial pressure of ammonia is said to be 0.85 atmospheres. And since at the very beginning, initially, we don't have nitrogen and hydrogen, obviously this is going to be 0. Then C represents the change in partial pressure. So if the change in partial pressure is said to be x, this x is going to be for nitrogen, and then since for hydrogen is 3 times the number of moles of nitrogen, then here it will be 3x. And then what is this? The change in the number of moles, we know that for nitrogen, since we have x and the number of moles ratio for ammonia to nitrogen is 2 to 1, then for this, the change is also going to be minus 2x. Why is it a minus? Because here, this ammonia is reducing and nitrogen is a plus and hydrogen a plus because these ones are increasing in concentration, meaning that their partial pressures are going to be increasing and the partial pressure due to ammonia is going to be reducing. Now we add E to represent the partial pressure at equilibrium. So at equilibrium, we are going to just be adding, get the initial plus the change. So this becomes 0.85 minus 2x. This is x and this is 3x. We are told that at equilibrium, the partial pressure of hydrogen was found to be 0.45 atmosphere. So at equilibrium, the partial pressure of hydrogen is 0.45 atmosphere. But then we know that at equilibrium, the partial pressure of hydrogen is 3x. So meaning that 3x is comparable to 0.45. Therefore, x is going to be 0.45 out of 3, giving us 0.15 atmosphere. So, therefore, the change in partial pressure is equal to 0.15 atmosphere. So the partial pressure of ammonia at equilibrium is going to be 0.85 minus 2 times 0.15. This is giving us 0.85 minus 0.3. And this is going to give us 0.55 atmospheres. So the partial pressure ammonia is 0.55 atmosphere. Then what is Kp is equivalent to the partial pressure of the products divided by the partial pressures of the reactants. So this is going to be the partial pressure of nitrogen divided by the partial pressure of hydrogen, times the partial pressure of hydrogen. And remember, this is raised to a power of 3. This is 3 divided by the partial pressure of ammonia. This is power 2 because that is the stoichiometric factor in the chemical reaction equation. So we are going to put in the values. The partial pressure of nitrogen, we know it. According to what we have here at equilibrium, we are going to be having 0.15. Then for hydrogen, is also known as 3x, which is 0.45 power 3, and then ammonia is going to be 0.55 power 2. Kp, which is the equilibrium constant in terms of partial pressures, is going to be 0.0452. So that is the equilibrium constant in terms of partial pressures. This problem requires us to calculate the equilibrium constant Kc. That is the equilibrium constant in terms of concentrations. So we are told that nitrogen monoxide and oxygen react together in a reversible reaction. 1.6 moles of nitrogen monoxide and 1.4 moles of oxygen are mixed together in a container with a volume of 4 decimeter cube. At equilibrium, 1.2 moles of nitrogen dioxide was formed. Calculate the Kc, which is the equilibrium constant, Kc in terms of concentration. So let's write the reaction for the chemical, let's write the equation for the chemical reaction. So this is how we can write the chemical equation for this reaction. So 2 moles of nitrogen monoxide are required to completely react with 1 mole of oxygen, giving us 2 moles of nitrogen dioxide. So we are told that the number of moles present at equilibrium, before that, we are told that initially, the concentration of nitrogen monoxide is equal to 1.6 divided by the volume. So since this is equivalent to 1 liter, so we are dividing it by 4, and this should give us 0.4 molar. So this gives us the concentration in terms of moles per liter for nitrogen monoxide. And then for oxygen, this gives us 1.4 divided by 4. So this gives us 0.35 moles per liter. And then at equilibrium, the concentration of nitrogen dioxide is 1.2 divided by 4 also. Remember that 1 decimeter cube is the same as 1 liter. So the concentration that we are getting is the molarity of those components. So now the concentration we are getting is going to be 1.2 divided by 4. This gives us 0.3 molar. This gives us the number of moles per liter of this volume. So that gives us the concentration that we need. Therefore, let's write our abbreviations ICE. Now at equilibrium, we have only what? Okay, let's first write these components. So we have values initially for nitrogen monoxide. We had 0.4 and 0.35 for oxygen gas. And then we shall have 0 for what? For nitrogen monoxide. Because initially the reaction hasn't taken place and therefore the product's concentration is equal to 0. Then the change in concentration after some time, we are finding out that this is going to be, for example, let's call it x. So if that is x, this is minus x actually, and this is minus 2x. That is the change. What has changed, okay, from 0.35, it must have reduced, whereas this side, it must be increasing. Remember, we are using a ratio of 2 to 1 to 2, meaning that if there is any change in number of moles of oxygen being negative x, okay, that means we are going to have the change for nitrogen monoxide as negative 2x, and the change for nitrogen dioxide is going to be plus 2x. So what is going to be the moles at equilibrium? This is going to be 0.4 minus 2x. and this is going to be 3, 5 minus x, and this is going to be 2x. But we are provided that at equilibrium, the moles of nitrogen dioxide are equal to 0.3 m, meaning that this 2x is equal to 0.3. So divide by 2, we shall find that x is equal to 0.15. So if that is the case, we want to determine the Kc. Kc will equal to the concentration of products, and the products that we are having here is only nitrogen dioxide, to power the exponent, okay, which is 2, that is being obtained from the stoichiometric reaction, divided by the concentration of nitrogen monoxide. This is also raised to the power of 2 times the concentration of oxygen raised to the power 1. So we already have the nitrogen dioxide concentration as 0.15 squared. Now we divide it by the concentration of nitrogen monoxide. Nitrogen monoxide is going to be 0.4 minus 2x. X or 2x itself is equal to 0.3. So this is going to be 0.4 minus 0.3. This is squared. Then we have for oxygen, oxygen is equivalent to 0.35 minus x. So if we get 0.35 minus 0.3, 0.35 minus 0.3, power it by 1. So Kc is 0.15 squared divided by, this is 0.1 squared times 0.05, and that is it. So Kc comes 45, and that is the answer that is required of us.